Suppose we have the ability to calculate the value of a function fx in any value of the independent variable x. Furthermore, suppose also that this function is well behaved in the range of interest. We can look for the derivative of f at a certain point. If f is known analytically, it is almost always possible to derive explicit formulas for the derivatives of f. However, on many occasions the analytical method cannot be used, although we can evaluate f from x. This may occur because of the need for some very complicated numerical procedures and not having an analytical representation, or worse yet, because the way we can generate f only provides its values in a discrete set, as those generated in a computer simulation. And to calculate the derivative analytically, the function must be continuous. So in these situations, we cannot analytically calculate the derivative of the function, but we can use numerical methods to estimate the derivative of the function. Suppose we are interested in the derivative on x0, that is, f prime of 0. This restriction is for the sake of simplicity, because we can get the same formulas for an arbitrary x through a translation. Let us also suppose that we know f in an equally spaced network of values x. This is illustrated in the image below with the points regularly spaced by h. Then, we will use the Taylor-MacLaurin series expansion to interpolate the function f. Prime indices denote the order of the derivative evaluated in x0. The exclamation mark represents the factorial of n. However, we cannot add infinitely. The series must be truncated at some point. By doing this, we make a mistake. The approximation will be better, the more despicable this error is. In other words, that we stick only with the most relevant terms for approximation in the selected range. We will use these definitions to obtain the formulas of the derivatives, as well as later on, of the numerical integrals. The number of points adopted will define the derivative formula. We can take 2 points, the same f0 and more or less another point, or 3 points, the f0, the next in the previous. The 3-line equal symbol denotes that the right-hand expression is a representation of the other left-hand one. We want to derive the two simplest formulas from number derivative, so let's start by taking 2 points, f0 and f1, which will compose the forward formula. Here, the O symbol of h4 indicates that we are discarding terms of order greater than or equal to 4. We also take 2 others, f0 and f-1, which will be the backward. What we will do is use the finite differences to get the formulas. Then from the first equation we get the formula of the derivative of 2 points forward by discarding the terms of order greater or equal to h square. We repeat the procedure to get the formula backward. We can analyze graphically what is happening. In both the backward and forward formula, we will consider that in the range between 0 and h, the function has a behavior of a linear function. We can compare these secant lines with the tangent line that graphically represents the derivative at the point. We can use either of the two formulas, the precision will be the same.